The first speaker is from Fastly, Lorenzo Zaino, and his topic is hashing on broken assumptions. Please welcome him.
Thank you very much. My name is Lorenzo Zaino. I'm a software engineer at Fastly. And the talk that I will give to you today is about flow-level hashing, and in particular is about assumptions on which flow-level hashing relies, situations in which this assumption breaks, and the consequences when this happens. So before jumping directly straight into the flow-level hashing, let's try to understand what is the problem we're trying to solve with flow-level hashing. Well, the problem is that we want to spread traffic across a multitude of network resources, such as paths, links, and hosts. And there are already a wide variety of solutions for addressing this problem, such as link aggregation and equal cost multipath. Link aggregation, for example, is a technique that allows us to combine multiple physical links between adjacent network devices into one single logical link. So, for example, let's say that we have two switches, and for convenience or capacity purposes, we want to connect them with multiple physical links. Well, link aggregation gives us the capability to abstract these physical links into one single logical link, which then gets showed to the upper layer. Equal cost multipath is another technique that we can use to spread traffic across paths, links, and hosts, and normally allows network devices which have got multiple routes to a given destination with the same cost to equally spread traffic across these different routes. Equal cost multipath is used normally in two main use cases. The first use case is to balance traffic across paths. Say that we got two endpoints with different paths across them, we can use ECMP to spread traffic across these different paths. ECMP can also be used to spread traffic across different hosts. We can have some set of any casted hosts, and we can route traffic to any of these hosts using ECMP. So all these techniques that allow us to spread traffic across devices and different network resources, they really need to meet two requirements. The first requirement is a load balance requirement, that is to ensure that all these network resources, so that the traffic is uniformly spread across the resources. And the second requirement is what we could call a stateless but sticky path pinning. That is to ensure that however the traffic is allocated, we need to make sure that all packets belonging to the same flow take exactly the same path. And we need to do so without requiring to maintain per flow state in network devices. Now, after I stated this requirement, I would like to spend some minutes to convince you why these requirements are important and what are the consequences if these requirements are not met. Let's start with loading balance. The main reason why you're interested in load balancing is that loading balance reduces system capacity. Let me show this with a simple toy example. Let's assume that we got a set of network resources, which can be hosts, paths, and links. And let's assume that we can uniformly spread traffic perfectly across the resources. That's what we have. We got traffic perfectly spread across resources. If the load on these resources increases, we can homogeneously increase the traffic across the resources and fully use all the available resources in our system. But what happens if we got some degree of load imbalance? Well, what happens is that we can increase the load only up to the level where the most loaded resources is fully loaded. But up to this level, we cannot take any further additional traffic because any additional traffic will make the most of the resource overflow. So we end up with a bunch of unused capacity over the least used resources, which is a very undesirable situation. We can actually quantify numerically what is the impact the load imbalance has on the available capacity. And to do so, let's recall the graph that I showed in the previous slide. Okay? And let's use some very simple notation. Let's define Lmax to be the load on the most loaded resources. And let's define Laverage to be the load, the average load across all available resources. Finally, let's define Umax to be the maximal attainable utilization, which is the maximum fraction of the overall system capacity which we can use given a certain load imbalance. So this practically corresponds to the red area as a fraction of the overall system area. Clearly, in an ideal situation, Umax is equal to 1. That means that the overall capacity of the system can be used. But as load imbalance increases, the maximum attainable utilization can decrease. It can get close to 0 if you got a very severe degree of load imbalance. In scientific literature, load imbalance is normally quantified as the ratio between the most loaded resource and the average load over the resources. Again, in the ideal case of perfect load balancing across the resources, this fraction is equal to 1, because clearly the load on the most of the resources is also equal to the average load across the resources, so the fraction is equal to 1. We can prove with very simple back-on-the-envelope calculations that there is a clear, simple relation between the maximum attainable utilization, Umax, and the load imbalance, expressed as a ratio between load max and load average. And this relation is that Umax is equal to the inverse of the load imbalance, represented as a ratio between load max and load average. It's not clear from this equation what the relationship, so let's actually try to plot this in a graph to try to understand better what is this relation. In the x-axis, I plotted the ratio between maximum load and average load, which is a quantification of a load imbalance. While on the y-axis, I plot the maximum attainable utilization, which is the maximum fraction of available capacity that we can use. Now, in the case of ideal load balance, Lmax over L average is equal to 1. And in this case, we can fully utilize all resources because Umax is equal to 1. However, if the load imbalance increases, the maximum attainable utilization rapidly decreases. If we take, for example, the case of the most loaded resources with 50% more load over the average resource, which, as I will show later in the presentation, is not quite an unusual case, we end up in a situation where we lose 33.3% of all our available capacity. So imagine that we got 200 servers, 66 servers are gone as a result of this load imbalance, which is quite of a severe problem. Now, hopefully I convinced you why load balancing is important. Let me try to convince you why it's important to pin packets belonging to the same flow, to the same path. So the consequences when we don't have path pinning depend on the kind of scenario that we use. Depends on whether we use ECMP or this technology to distribute traffic between different paths but within the same endpoints, or we use to split traffic across different points. So in the first case, where we use our techniques to balance traffic across different paths but between the same endpoints, not pinning packets to the same path causes out-of-order packets, which as a result can be interpreted by TCP stacks as signal of congestion, and will cause TCP senders to drop repeatedly the congestion windows, and that will cause a poor TCP performance. Clearly, this situation is very undesirable. However, the situation is way worse if we want to split traffic across different endpoints. In this case, not pinning packets belonging to the same flow, to the same path, will cause TCP resets. Let me show you with a simple example when TCP resets can arise and what are the consequences. Let's assume that the host on the left-hand side wants to communicate with any of the two hosts on the right-hand side. And in the middle, we got a router which has not pinned packets belonging to the same flow, to the same path. Well, the host on the left-hand side starts a TCP handshake, sending a SYN. The host will reply with a SYN and an ACK. Then the host will send an ACK, which will be forwarded to a different host. But now the host on the bottom does not have any socket regarding this connection. So we'll send a reset back, and the flow will be interrupted. And so the flow will not be able to progress, which is a very undesirable situation and will break connections. So there are two main requirements, as I discussed. I'm not sure why there's another line. So these two main requirements are load balance and path pinning. And there is the de facto standard solutions for addressing this problem without requiring flow level state is flow level hashing. Okay? So flow level hashing simply works as follows. Let's assume that we got an input packet, okay, that is provided to a network devices. The network device will read the 5 tuple out of this packet and will extract them, which are source and destination IP address, protocol, and source destination port. Then it will compute a hash function on this 5 tuple and will compute an X top that is used to forward traffic. Okay. This flow level hashing is predicated upon two assumptions: that flowing based on the packet 5 tuple will ensure a uniform spread of load across nettops, and that hashing again on this 5 tuple will ensure that packets belonging to the same flow are pinned on the same path. However, we should question, do these assumptions really hold? Well, we're going to find out. Let's start discussing the first assumption, which is the load balance assumption, okay? So we assume that hashing uniformly spread traffic across next stops. Let's see if this happens. So we at Fastly have been using ECMP for many years, extensively. And at a certain point, we encountered a situation when we found some occurrence of load imbalance, which seemed only to appear in a certain, only using specific network devices. So we wanted to experiment and prove our conjecture, and we performed a little experiment. So we used two different network switches, and we set up each of these switches to have 256 next stops. So we set it up with a route with 256 next stops. Then we sent to this router a combination of various packets with different 5 tuple, and then counted how many of these packets ended up to each of these next stops. I'm now going to show you in this graph the results that we got. On the x-axis, I show the next stop rank, which is the next stop ranked for in increasing order of packets received. So the leftmost next stop is the one that received the least amount of packets, and the one on the right is the one that received the greatest amount of next stops. And on the y-axis, I showed the load, the number of packets that each next stop received, normalized by the average number of packets received by any next stop. Now, in Nadir's case, this would be the graph that you would expect. We would expect each next stop to receive exactly the same amount of packets. That indicates a perfect load balancing. In the case of switch A, the measured results was pretty close to the actual intended results, to the point that we could not really distinguish the plot of perfect hashing and the measured one. However, the situation was a bit different with switch B. This was the switch that introduces some level of balancing. The measured results in this case was pretty different from expected. And as you can see from this graph, the difference between the most loaded next stop and the average loaded next stop is 50%. And there was also a 6-fold difference between the most loaded and the least loaded bucket. If you recall the graph that I showed you earlier on, in a situation like this, with the most loaded next stop with having 50% more traffic than the average next stop, that would have caused a loss of 1/3 of our capacity. So a situation like this would really cost a large amount of capacity. Switch B also had an additional problem because it was supposed to support an arbitrary number of next stops between 1 and 256, as I can show in this table. However, the situation in reality was a bit different because only a subset of next stops were actually supported. So it turns out that if we try to select a number of next stops which was not supporting, say for example 126, only 120 next stops will receive any traffic at all. 6 of these next stops will not receive any traffic, which further exacerbate the degree of load imbalance that we experienced using this switch. Again, hopefully I showed you that load imbalance assumption not always holds, even on commercially successful switches. Let's now talk about path pinning, and let's discuss whether hashing on the 5 tuple really maintains 5 pinning. One thing that can really break path pinning is hashing on the IPv4 type of service field. So as I discussed before, normally, out on IPv4 header, we should normally consider protocol, source and destination address in our hashing decision. However, we found out that certain routers around also hash based on type of service. Why would this router do this? Well, they would do this because originally that was specifically permitted by RFC 1812, which specifically permitted using the type of service diffserv field in routing decision. This, however, was 22 years ago. Recent RFCs changed the situation. For example, RFC 2474 deprecated the type of service field and redefined it to be a differentiated service field. But what really made the type of service field an unsuitable field for hashing on is RFC 3168, which reserved the latest 2 bits of the type of service octet for ECN-capable definition. So, and with this RFC, we can no longer guarantee that packets belonging to the same flow will always have the same type of service field, because they will change throughout the flow. And let me show this with a very simple example that we experience in practice. On the left-hand side, there's a host that wants to communicate with any of the hosts on the right-hand side, and all of these hosts are ECN-capable. And the router hashes based on the IPv4 type of service field, as allowed by RFC 1812. So the host on the left-hand side initiates a TCP connection, and that gets hashed to the topmost host. During a TCP handshake, the ECN-capable bits of the type of service field are left unset because the ECN capability has been negotiated. But after the handshake is completed, then the ECN capability is negotiated. The host on the left-hand side sends the flow data, including setting to value 1 to the ECN-capable bit. The router then takes this bit into account in hash calculation, and that ends up on a different host, therefore breaking the flow. We actually experienced in practice this issue towards the end of 2015, when Apple started enabling by default ECN on iOS and on SX. And we observed an increased number of resets, but we observed that this was only happening on a specific paths. And we identified that certain operators were deploying some routers that had this behavior. We had to solve this problem. The only way that we could solve this problem was to disable ECN on our side. And unfortunately, I have to say that routers in the wild that hash based on a IPv4 type of service field is actually one thing that makes ECN pretty much undeployable at this time. So we talked about an IPv4 specific issue. Let's talk about an IPv6 one specific. So we received this a few months ago. We observed a few months ago that there was an increased rate of resets in our network coming from IPv6 packets from a specific ISP. We did some investigation, and we found the middle box, which has quite a remarkable behavior. So this middle box was performing the following thing. If it received a packet with a flow label which is equal to 0, it will forward the IPv6 packet unmodified without making any change. However, if this IPv6 packet had the flow label with a different value, the value which is set different than 0, it will rewrite this label to a value which looked random to us, which varied across different packets of the same flow, which, by the way, is specifically forbidden by the RFC 6437. On the other hand, on our side, we had a switch which was using the IPv6 flow label for hash computation, which is instead allowed by RFC 6437. And this is the situation where we had. We had the host on one side wanted to communicate with any host on the other side. So the first host starts sending an IPv6 packet with the flow label x, with x equal to 0. That gets randomly written by this middle box to a value y. And then the switch uses this value y in making its forwarding decision, and then the packet lands on the first host. Then the host sends again another packet with the same flow label, different from 0, gets rewritten to another random value y, z. This value gets taken into account by the switch and ends up on a different host, and the flow is broken. Unfortunately, this situation was aggravated by the fact that we were not able on our side to disable hashing on the IPv6 flow label, because this was not a capability that our vendor exposed to us. So the only way we had to fix this problem was to go back to the middle box operator and ask them to flash and do the firmware upgrade around their middle boxes. Finally, another situation that we had was caused by SIM proxies. So there's a cloud provider which uses SIM proxies to establish outgoing connection. So whenever a host wants to establish a TCP connection to the outside world, it will request this SIM proxy to create the TCP connection and create the handshake on its behalf and return the connection back. On the other side, these are us, where we have a set of switches connecting a fully bipartite topology to a set of hosts. And all these switches have either one of these characteristics. Either they use ingress interface for hash computation, or they're configured using different seeds in the hash function. That's what happened to us. The host on the left-hand side wants to set up a TCP connection, so we request the SIM proxy to do so. The SIM proxy will then make a route lookup, will have different routes available, and will pick up, let's say, the switch on the top side, okay? The switch then will pick up the first host and will establish the TCP connection. The SIM proxy then will return established TCP connection to the host, which can then start sending data. So the host, again, does a route lookup. But the host might have a different set of routes available, may have a different hash seed, may have different characteristics. It is not guaranteed that we'll pick up the same route. And in that case, we're actually picking up a different route to the switch. Now remember, this switch could correct the situation if it was hashing the same way of the switch above. However, that was not the case. It picks up the second host, and that breaks the flow. And again, in the situation, we got the same problem in the case before, that we were not able to configure our switches to either use the same hash seed across the whole deployments of the switch, and we were not able to disable using the ingress interface in hash computation. So the way we had to solve this problem was to pin the BGP connection, the BGP session with our peer only to one specific switch, to ensure that all traffic will come only to one specific switch. So this concludes a bit my presentation. If we could draw a set of conclusions out of this presentation, I could say that, well, that the load balancing assumption is sometimes broken. Sometimes devices do not hash uniformly, and you should not probably write on it. Another thing, probably more importantly, I would say that hashing on any field which is different from the type 5 tuple can and will break ECMP. So hashing on fields like ingress ports, a IPv4 type of service field, or a IPv6 flow label has the potential to disrupt ECMP. Finally, if you can distill this conclusion into a set of recommendations, I would say to operators, they should probably ensure that your network devices hash flows uniformly. Otherwise, they could reduce your available capacity and cost you money. And also, I would say that unless you have a specific reason for enabling hashing on other fields except to the 5 tuple, or you don't need any extra entropy, you should probably maybe consider disable that, because they might break flows downstream. And finally, if I could give some recommendation to vendors, I would say that it could be probably advisable to expose to your customers the availability to configure the seed of your hash function, and also give the possibility to disable hashing on different input apart from the 5 tuple, and probably leave them disabled by default. So I understand the switches normally are shipped with a configuration which is more suitable for the desired use case. However, switches are normally used for use case different from the intended one over the time. And maybe in this case, it's probably an advisable idea to disable hashing on this field by default on all your switches. So this concludes my presentation. I would like to thank you very much for your attention, and I'm happy to take any questions you may have. Thank you very much.
Hi, Chris Woodfield, Salesforce. I know that there's a number of switches now that have more advanced hashing features, mainly based around achieving consistent hashing, based around consistent hashing algorithms, ring hashing, resilient hashing, different vendors call it different names. Did you, in your testing here, were you able to evaluate any of those feature sets, and did you see any different outputs than what you reported in your presentation?
No, we did not test it with consistent hashing, but is it my understanding that normally consistent hashing is actually built on top of traditional hashing, so it's the same layer of abstraction on top of that. So unfortunately, I don't have the data. I cannot tell you if this will happen also with consistent hashing, but if I had to make a guess, I'll probably guess that we will have pretty much the same behavior.
Okay, thank you.
I don't have any data, unfortunately.
Matt Petak, Yahoo. So if you've got a switch vendor out there that claims it can hash on up to 256 values for your lag bundle or ECMP, and yet it's consistently and repeatedly not hashing on that, is this something that the vendor confirmed was a bug they were fixing, or is this a hardware flaw that it might behoove you to share some information with the rest of the community on? Beware this hardware platform, it will screw you over.
Okay. I didn't mention the specific platform, and I don't know.
Well, I'm curious, did the vendor that you talked to, I assume you went to the vendor and said,
yes,
this looks really broken, is it fixable? Did the vendor tell you if it was fixable?
We didn't go back to us on this one, so
okay,
we
thank
reported
you.
to the vendor, though. We didn't have any follow-up.
Let's go.
Joel Yegley. I'm not here to sandbag you, given that we do work for the same company. But I think there's an interesting punchline to the flow label thing, right? Because when we started with flow labels, they're supposed to be unique when you create them, except of course that you can mostly set them to 0 and get away with that for a number of years. Then the IETF came along and decided that we should rehabilitate the flow label a little bit, and one of the potential use cases for it, of course, was load balancing, which of course, because it's not immutable and bugs in the internet could change it, seems to be a bit of a problem. I personally don't see us being able to ever use the flow label for load balancing. I wonder what your thoughts are on that.
I agree with you. Yeah. I mean, to be honest, it's probably better having some degree of load imbalance than breaking flows. So, yeah. So at least,
Well, it's kind of like packet coloring. If I thought it was dangerous at any speed, I'd probably choose to sanitize them, like as they were leaving my network, so that I wasn't inadvertently responsible for creating this mess for someone else, right? And I don't think that's a recommendation that like we as operators would make to the IETF, or at least not one that would be well received. Sanitizing all your flow labels. But I would be sort of deeply concerned that this sort of thing can happen on accident, and people don't necessarily notice
I agree.
until we shoot ourselves in the foot with it with stateless load balancing.
It's Phil Bidar from Cisco. Have you approached vendors more about user configurable hashing, and like how much, what kind of inroads have you made with getting vendors to support those types of functions?
So yeah, we've been talking to vendors and we set forward some feature requests, and some of them slowly been addressed. But yeah, we still don't have full capability on all our fleet to fully configure the hashes as much as we want, and we would like to have more actually. So.
Good evening, Joel Stepman, Juniper Networks. One of your first slides showed an example of load imbalance and how that can affect the total throughput.
Yep.
Haven't actually seen that. I mean, the networks I work on and the hardware I work on load balances very well. And if you have a large number of users, it generally balances out pretty well. But let's say for the fact that it didn't and you actually had that, what scenario, or I guess why do you assume or say, or what scenario would lower the maximum attainable utilization over all links because one link is full? I mean, I would expect that if you're hashing to TCP UDP and you have a fat flow, that fat flow is going to slow down. But if you have 1 million subscribers or even 100,000 subscribers, the other ones aren't going to know or care. Everyone who's hashed across the other links, I would expect them to be fine. Can you elaborate as to what scenario, do you see this often? What scenario creates this, and why are other, I guess, why do you see the max attainable utilization actually being capped?
Okay, so in this case, for example, let's say maybe the case is in my interest. For example, we use ECMP to hash across servers, right? Servers can take a maximum capacity of traffic, right? So the more capacity, if we reach a CPU capacity, sorry, let me rephrase. We're actually bound by the CPU capacity that takes to process the flow, right? So if we got some degree, something that gives us a level of imbalance, that's pretty much the situation where we are, right? I'm not sure if I answered you.
Okay, now, I realize my perspective is always, I always look at ECMP within a network, so router to router, switch to switch. I had a second question about hosts. So I guess if you see this in a switch or device to end host perspective, and I have seen that with Microsoft's old SLB, where you were limited to one link utilization, but I don't see that being a common problem anymore.
Well, but if you have a problem, let's assume that for some reason you got this level of imbalance. So I showed him that the slide that it was caused by some issue in the hashing. But
ECMP imbalance is a common issue. We see it frequently in networks. It's not unusual. He's right.
Okay. Thank you.
Yep.
Oh, sorry, can you elaborate, because I have...
If you've got large server clusters or storage clusters in data centers and you're replicating between data centers, you will see flow situations like that, where you're hashing onto 1 out of 8 links in a bundle or 16 links in a bundle, and you're looking at it going, well, shit, I just can't pump any more across because I'm just flatlining that link more and more and more.
Well, yes, and that part, if you have the fat flow problem, you're always going to have. Your fat flow can never exceed the link speed of your member links. But that does not necessarily, and that will impact all other customers on that link, but I have not seen that impact customers that are hashed across links 3 through 8, which are going to be different servers, or at least different flows.
It's a little hard to say, all right, now everything else in the network, make sure you hash on the other links because this guy's really full, and unfortunately, you're going to have other traffic hashing onto that. So what you have is your elephant flow starts crowding out. In this case, it would be 25% of your non-elephant flows as well.
Yes.
And so you've got 25% impact across your flow base. This is not a happy situation for a network to be in.
Oh, I agree with all that, but there is still, the other bandwidth can be utilized. You still have impacted customers. but there's-
You can't magically change your hash algorithm on the fly to say, more if you go over here. That's the problem is you can't tell the network, go use the unused capacity. There's no magic knob that does that on the fly.
Well, there is that I have not personally had to use because we don't have this problem in my customer's network. But
Do tell us about the magic knob, because I love magic knobs. I want more magic knobs in my network.
I don't want to hijack this conversation, but talk to me afterwards and we'll talk about it.
All right. If he tells me about a magic knob, I promise to share it with the community, because I think we all need more magic in our networks.
Okay.
I think my time's over.
Out of time.
Yeah, just
Thank
to
you.
respond to that quickly, I think the law of small numbers sort of applies to the distribution of very large flows in this case. But you do actually get into consistent situations where you become unlucky, for lack of a better term, and yeah, everybody else on the link is fine, and the lag bundle itself is running at 30% utilization. But the distribution of traffic is such that the bundle, or the portion of the bundle that has 10% of the traffic on it, continues to get more flows because, well, that end of the hash distribution is continuing to, get a slightly higher percentage of all of the flows than the other members of the bundle, right? So that's kind of cool in the sense that if you alarm at like 50% or 70% utilization on your links, you might want to also alarm at 20 or 30% utilization where there's 100% utilization on one member, right? So if you have 32 member lag bundles, like you can get unlucky. That's definitely a thing that happens. And you'll be like, well, it's not being heavily utilized, except a small part of it is.
Agreed, understand.
Thank you so much for the audience participation, and thank you for the speaker.